This will be the second exercise in our Module 6, Lesson 6 on graph optimization. It says that the weighted graphs in the figures here show some major roads in New Jersey. So the first image that we'll see, the edges of the graph are weighted by the distance between the cities. And then on the next page, we'll see the same graph where the edges are weighted by the cost of the tolls to travel on the roads from city to city. The question asks us to find the shortest route in terms of distance from Newark, New Jersey to Camden, New Jersey, and from, this is just a typo, it should say, and from Newark, New Jersey to Cape May, so that you travel to all the other cities using these roads. So if we were following the closest neighbor algorithm, well, my first choice is always going to be to move from Newark to Woodbridge, 20 miles. But the closest neighbor algorithm would send me to Asbury Park, which would be 35, then to Trenton, another 40 miles, and then I'm in Camden after another 30 miles, but I have to travel to all of the cities, so I can travel to Atlantic City, Cape May, and back to Camden. So 45 and then 85. So if I put this all together, then I've traveled a total of 310 miles from Newark to Camden. Instead, when I'm at Woodbridge, if I don't make the closest choice, so let's just say I go ahead and travel to Trenton, so 20 miles and then 42, then to Asbury Park, 40 miles, then to Atlantic City, Cape May, and then to Camden, so 75, 45, and 85, then the total is 177, 182, 222, 307. So this is actually a quicker path to travel to all of the cities and get from Newark to Camden, but I couldn't find it using the closest neighbor algorithm. So Newark to Camden. Then I also am to travel from Newark to Cape May, stopping in all of the cities. So again, my first choice has to be from Newark to Woodbridge, 20 miles. Then this will send me to Asbury Park, and then to Trenton, Camden, Atlantic City, and then to Cape May. So my total trip from Newark to Cape May is 230, I think, 55, 95, 130, 185, 190, 230, right. And I've still traveled through all of the cities. I did this following the closest neighbor algorithm. And in fact, to visit all of the cities, this should be the shortest distance to travel from Newark to Cape May. So you can see that depending on the choice of the city that I need to end up in, it can make a significant difference in the amount of miles traveled. I've still visited all of the cities, but because of the way that the roads connect the cities, it was much more efficient to end up in Cape May. So that's one thing to consider. Now we have the same roadmap but in terms of the toll roads and what it would cost to travel from city to city, and we're going to plot the same travel. We're going to look at going from Newark to Camden and visiting all of the cities, as well as from Newark to Cape May. So first, we travel from Newark to Woodbridge, 60 cents. And following the closest neighbor algorithm, that would take us then to Asbury Park, 75 cents. Then it doesn't cost anything to get to Trenton. Then we would spend 70 cents to get to Camden. Now, the cheapest road to take would be back to Woodbridge, but this is a city we've already visited, so our algorithm would tell us next we would go to Atlantic City, and then to Cape May, and back to Camden. So all in all, we'd have $4.05. And this does look like the cheapest that we could go. The other path that we took last time was to go from Newark to Woodbridge, from Woodbridge to Trenton, and no, in fact, I think that might be less expensive. Let's try that. So we could go from Newark to Woodbridge, which is going to be 60 cents. Then from Woodbridge to Asbury Park is 75 cents. Asbury Park to, we go to Trenton for $1. Then to Camden for 70 cents. Then we'd go to Atlantic City, Cape May, and back to Camden. So that's going to be 60 cents, $1, 70 cents, $1.25, 75 cents, and 0. So it does end up being cheaper to go this way. Okay, so that's our cheapest route to end up in Camden. Now, we can also travel from Newark to Cape May. So, of course, we first travel to Woodbridge, 60 cents. Then travel to Asbury Park, then to Trenton, Camden, Atlantic City, and Cape May. This is also 405 because it's exactly the same trip that we took here, except for the cost then to go from Cape May back to Camden is $0 here. On the previous slide, we saw that it's something like 85 miles, but there's no toll road there, so it's not costing us anything extra. So this is the cheapest way to get from Newark to Cape May by visiting all of the cities. And we were able to find it using the cheapest neighbor algorithm. And in this case, it was actually the same price to travel to Cape May as it was to Camden, even though the trip would have been a longer distance, as we saw in the previous exercise. Okay, we're again going to apply the closest neighbor algorithm in exercise 3 to find the minimal circuit based at Toledo. So because it's a circuit, we know we want to start here in Toledo and end in Toledo. And in each step of the process, we're just going to choose the closest city to travel to that we haven't already visited. So the first city, or the first route, will be from Toledo to Detroit, and that edge has a cost of 58 miles. Then from Detroit, I can most closely get to Saginaw, and that edge has a cost of 98 miles. Then the closest city here is to go to Grand Rapids, 113 miles. From Grand Rapids to Kalamazoo is 56 miles. That's the closest city. And then back to Toledo will be our closest choice here. So according to this algorithm, the best way to visit all of these cities and return to Toledo would be to just go around this perimeter instead of zigging and zagging back and forth. And in total, our trip would be 458 miles round trip from Toledo back to itself. Now, consider the network whose maximum capacities are shown in the following graph. So this is a network. Just to make it easier to talk about, let's assume that this is like the city water system as we saw in the lecture. The question tells us that a function f is partially defined on the edges of the network by f from source to C equal to f from source to B equal to f from source to A equal to 2. So what does that mean? That means if I'm sending 2 gallons or hundreds of gallons or thousands of gallons, whatever the measurement is, but I'm sending 2 from source to C. So I'm going to use this notation, this fraction notation, to make it look like it's 2 out of 3, because 3 is the weight of the edge, or the maximum capacity of the water pipe. And from source to B is also 2, and from source to A is also 2. Then from A to D is 1. Then it asks us to define f on the rest of the other edges so that f is a flow. Then what is the value of f? So we should be able to deduce this. First of all, if I send 2 gallons to vertex C, then 2 gallons have to come out of vertex C, and vertex C is only connected to vertex D, so they must flow through this edge here. And similarly, I sent 2 gallons to vertex A. One of those gallons got diverted towards D. That means that one of them is still flowing here through G. And G is the only edge, or the only vertex, connecting this way to the sink, so this must also be 1. So then, what I sent through vertex B is 2 gallons. That must be here on the other side, too. But now if we add up, because we diverted this 1 gallon from A to D, I'm going to have 5 gallons flowing out of D. So the rest of the function, I need to say that f from C to D is 2. F from B to D is 2. F from A to G is 1. F from D to the sink is 5. And F from G to the sink is 1. So now I've assigned a value, a function value, on every edge of the graph. That's part A. And then it asks, what is the value of the flow? The value of the flow is just the amount, it's both the amount leaving the source and the amount entering the sink. So the value of the flow is 6 in this case. Then part B asks us to find a flow augmenting path with respect to F for this network. And what is the value of the augmented flow? So what I need to look at in order to find a flow augmenting path is where in this network do I have additional carrying capacity. So for example, if I look way over here, where I'm going into the sink on this side, I clearly see that there's extra capacity here. I could send up to 5 more gallons through this way. Although it's not always true that I'm going to be able to meet the maximum capacity, but it's possible in some cases. So this might be a good target. I want to see if I can send more flow through here, which would mean sending more through here, which would mean sending more through here. So what do? I will look at the difference between the capacity or the weight of the edge and the current flow. So I say the weight from G to the sink minus F from G to the sink, or the flow. Well, that's equal to 6 minus 1, and that's 5. The weight from A to G minus the flow from A to G is equal to 3 minus 1, which is 2. And the weight from source to A minus the flow from source to A is going to be 5 minus 2, which is 3. So I collect all of these bits of information and I choose the lowest number. The minimum here is 2. So that is how much I can augment the flow by. So I can augment the flow by 2 all along this flow augmenting path. So my flow augmenting path is source to A to G, G to sink, and I can make this 4 out of 5, 3 out of 3, and 3 out of 6. So the flow augmenting path is source to A to G to sink. And the value of the flow, or the augmented flow, the value of the augmented flow is the previous flow of 6 plus the augmentation that I did was 2, so it's 8. Another way to know that it's 8 is just to add 5 out of 6 plus 3 out of 6. So I have 8 out of the maximum possible 12-gallon flow. Now I did mention that there were other possible flow augmenting paths. For example, I can see that I can send another gallon from source to B, and from B to D, and from D to sink. So this is not the maximum flow. Question C asks us if this is the maximum flow, and we'll say this is not the maximum flow. And that's because source to B to D to sink is another flow augmenting path. If we wanted to find a maximum flow, we would need to examine all of the possible flow augmenting paths. Okay, in the next exercise, we have a network with capacity function C and flow function F. And in this case, we do want to find the maximal flow function. In this case, the labels on the edges of the network are already in this fraction form of the flow divided by the maximum capacity, or the weight. So what are we looking for? We're looking for flow augmenting paths, possibly more than one. So if I look at S to A, source to A, I can see that I should be able to add one here. And from A to B, it looks like I have room to add one, and from B to sink, it looks like I can add one. So this is a flow augmenting path. Source to A to B to sink. It's one possibility. I want to notice here that the maximum possible flow would be 12, because I have a capacity of 7 and a capacity of 5. I also have a capacity of 8 and 4 here on the entering side. So I have a maximum possible capacity of 12. Now, it's not always possible to achieve the maximum flow of 12, but in this case, I think we probably can. We already have, right now, this initial flow, which came from the function f, is 10. And I know that I've already found one flow augmenting path where I can add 1 gallon of flow. Now, if I look at the edge from C to sink, it's clear that this is already at the maximum capacity. So I'm not going to be able to send anything there. I'm going to have to instead divert the flow so that it goes from B to sink. But I'm also already full this edge from C to B. So what I can do is use this edge in reverse when I'm looking for my flow augmenting path. So I'm going to say from source to C. Then it looks like I am able to use this flow augmenting path backwards. I can use this edge from C to A backwards. Then I can go from A to B and from B to sink. So the rule said that when I want to find the flow augmenting paths, I'm going to find the minimum of the weight minus the flow, or just the flow if it's being used backwards. So now what I'm looking at is the weight, or the capacity of source to C, minus the flow of source to C, and that's 4 minus 3. Then I'm looking at, for the edge from A to C, I'm just looking at flow from A to C, because I'm using this edge backwards. This is 4. Then I'm looking at the weight or the capacity from A to B minus the flow from A to B, which is 6 minus 3, which is 3. And then I'm looking at the capacity from B to sink minus the flow from B to sink, which is 7 minus 5, which is 2. And this is to determine how much I can send through this path. I can do the same thing with the other flow augmenting path that I found, which was I can find C of source to A minus flow of source to A. And that's 8 minus 7, which is 1. I can find C of A to B minus flow of A to B, which is 6 minus 3, and that's equal to 3. And C of B to sink minus flow from B to sink, and that's 7 minus 5, 2. So the minimum here is 1. The minimum here is also 1. So what that tells me is that through each of these flow augmenting paths, I can send 1. And I just want to be a little careful because they are using part of the same path from A to B to sink. So if I look at the numbers from A to B to sink, I just want to make sure that I actually have enough room to send 2. And I do, because the minimums there are 3 and 2. Or the numbers there are 3 and 2, the minimum is 2. So I have enough to send 2. I found these 2 flow augmenting paths, and this is how I determined how much I could send. If I was wanting to use the edge in the forward direction, I did the weight minus the flow. If I was wanting to use the edge in the backwards direction, I just did the flow. Okay, so if I send 1 gallon from source to A, I'm getting a little crowded up there, so I'm just going to recreate this network. So my capacity is 8. I had 7 out of 8 already. I'm sending 1 more, so I'm going to make this 8 out of 8. Then my capacity from source to C was 4, and I already had 3, and I want to send 1 more, so I'm going to make this 4 out of 4. So I am operating at the maximum capacity. Then from C to A, I was sending 4 gallons from A to C. I'm only going to send 3. So I'm going to make this 3 out of 5. So I subtracted 1 from here. Then from C to B, I didn't change anything. This is still going to be 2 out of 2, so I'm not using this in my flow augmenting path. And from C to sink is still 5 out of 5, not using this in my flow augmenting path. From A to B, I added 1, so this becomes 4 out of 6. And this becomes 5 out of 6. I added 2. I added 1 from source to A and 1 from source to C. And then I have 7 out of 7 coming out of B. Now, if we were to check them all, in order to determine that this is a valid flow, we would need to make sure that the difference between what's going in and out of each vertex is 0. So what flows in must flow out. And we would need to make sure that everything that leaves the source enters the sink. And I think we could briefly examine this and determine that that is true. I have 8 gallons leaving the source and headed towards A. I send 3 of them this way and 5 of them that way. Then I have 4 gallons coming in. 2 of them head towards B. The other 2 get added to the 3 that are coming down from A, and they head towards the sink. So this is a valid flow, and it would be defined as, I would call it maybe F2 now. F2 from source to A is 8. F2 from source to C is 4. F2 from A to B is 5. F2 from A to C is 3. F2 from C to B is 2. F2 from C to sink is 5. And F2 from B to sink is 7. The value of the flow, and this is the maximum flow, is 12. So this is the last exercise on the lecture note for Module 6, Lesson 6. So we'll stop the video here, and the next lesson will be Module 6, Lesson 7.